Okay, so let me go further. Okay, so let me tell you a story, right? And if you know the story, then you would appreciate what I meant. Okay, right? So it was just early 20th century, means 1900. Okay, around 1900 that time. Okay, uh, right. So around 1900, there was existing physics laws. Okay, okay. Let me use, maybe probably I'll use my hand notes also, right? So existing the physics laws around 1900. Okay, right? So what are they? Right? We will not bother too much. We'll just list down few which were very important. So there is something called electrodynamics. Okay, or you may say electromagnetostatics. Electromagnetostatics. Probably it is there up to certain extent. Okay, and there is a thermodynamics, right? Okay, and there is a Newtonian laws, right? And anything derived from them, their derivatives. So basically, these are the sorry, the branches of physics which were developed by 1900. Okay. Now, what happened? The experimentalists are not keeping quiet. They don't care what is the theory being developed. What they did, they do experimentalists. They do experiments. What they are best at, experiments. Okay. For them, it's not an issue. No need to know anything, any theory. Just take an experiment, okay, and just execute the experiment, make the observation. If they try to understand the observation, fine, well and good. If not, what they do, they just publish the result and ask the theoreticians to do the job for them, and ask the theory people, please see, these are the observations I am getting with from my experiment, okay, and explain why these things are behaving like this. Okay, now the experimentalist job is very easy. Do the experiment very carefully, make authentic observations, and then publish the result and seek the analysis and explanation from the theoreticians. Okay, now the theoreticians has to worry why these things are behaving like that, and they have to explain why these things are behaving like that. Okay, right? One of such experiment done before 1900 is, okay, you take a solid, let's say solid iron or rod, okay, right? It's a solid. Burn it or heat it to a very high temperature, okay, and just see what is the energy. Then just make an observation or just see what kind of radiation emitted by this hot iron object. Okay, so they just did this, okay, and they found the radiation coming, energy is coming out from this iron in all the frequencies. I'm sorry, in all the frequencies. Okay, what I mean is, if you just plot frequency versus intensity of the light, okay, not I means not a current, it's a intensity. I'll write down for you. Okay, and what they observed, for every frequency there is some intensity coming out. Okay, right? They only took a iron made like a metal iron made up of ferrum. Okay, right? So they took it and they burn it. They heat it to a very great higher temperature and they just making an observation. Now what they saw was continuous band of frequencies. Not even many frequencies. Continuously for every variation in the frequency there is some intensity coming out. So it was some kind of a bell curve. Okay, right? Let's say for some t is equal to very high. Okay, I will say very high. Let's say 5000 Kelvin. Okay, probably they thought, okay, maybe temperature is very high, that's why I'm getting all the frequencies. Let's reduce the temperature and make observation. Again, continuous and so on. Okay, that is why I see some continuous band of frequency intensity. Let's do one more thing. Let's take a box, a three-dimensional box. I mean, okay, take a box, empty the box. Inside the box, you put a metal films around. Okay, nice thin metal films you put and heat the metal films in such a way inside a gas is there and they heated the metal films, everything inside. Okay, some temperature is added and they took a small hole. Okay, such a way that let's say a radiation is emitted from one wall, goes and hits the other wall. Now the film is, let's say, made up of nice shining reflecting mirror film. What happens? Either the incident light takes some energy from the other hot region and then reflects back. It does multiple reflection. After some time it aligns to the hole, obviously, and will get some radiation out. Okay, right? So this is like a small cavity, means small region. Within that, I'm going to heat and generate the radiation. Okay, right? So now you see in both the places I have metal involved. Only thing is on the left side I have a solid which is being heated. On the right side also solid being heated in a very thin film. Okay, right? So and they just checked what is the radiation distribution would look like for corresponding to this kind of a heating mechanism. Okay, interestingly what they found this time is there are particular frequency lines. Let's say small peak here, there is another small peak here. Okay, likewise there are few peaks they were seeing, very thin peaks, intensity of light. Okay, let's say there is a corresponding to green light, red light and blue light. Okay, something like that. Fine. So what they saw is very interesting. Earlier I was heating a solid, I get a continuous band of energy. Now I am getting discrete bands of energy, means frequencies are nicely separated in terms of intensity. Okay, let me show you for a effectiveness. What they saw is this. Okay, you see, for 7000 Kelvin, we have a band structure. Okay, this one is some band intensity. Even for 6000 Kelvin also they saw that. 5000 Kelvin. If you reduce the temperature, the intensity is going down and down. Obviously, there may be no intensity if the temperature is very, very low. Okay, fine, that is fine. And now, when you take a box, within the box, you make a thin films around the surfaces, faces of inside surfaces, and then heat it and take the temperature, sorry, radiation out. That radiation, if you measure, whatever I was explaining with my hand notes, that was shown here in the form of, you see, discrete spectrums. Okay, so there is a red light, there is a blue light, okay, right, and there is a green light, yellow, okay. And you can ask me a question, why did you draw red first, blue later in my plot? You can ask this question to me. Please remember, I was plotting with respect to frequency. When it comes to the figure over here, what I was showing, with respect to lambda, it is showing. You know that the frequency and lambda are inversely proportional. Okay. Larger the wavelength means smaller is the frequency, smaller is the energy. Okay. Smaller is the wavelength, larger is the energy. That's why blue light is the more intense energy wise. Okay. So that is what I am actually depicting in my IV characters, like a intensity versus frequency of this radiation coming from this black box. People call together this entire setup as black body radiation. Okay, right? What I mean is, okay, whatever energy we are supplying, we are trying to take all the energy out without being wasted. It's like a perfect black body, people call, na? It takes all the light. Okay, it doesn't emit any light. That's why it appears to be black. Okay, so that is a black body radiation. This is the experiment, set of experiments done by experimentalists before 1900. They just given to the theoreticians, please explain why it is so. More or less, both the cases I am doing heating the solid. Okay, right? Now, that is the time the theoreticians started scratching their head. How do I explain this process? You know why? The problem is both scenarios appear to be same. Why two different results? Okay, right? Okay. So to explain that, there are some scientists, physicists came along. Okay, we are not getting into the too much details. So it's too much of statistical physics, thermodynamics, too much of solid state physics. A lot of physics is involved. Since in 1 hour I have to convey the idea of quantum principles, I'll just take the essence what actually being done around 1900 onwards till 1925, about 25 years time. I'm just telling you the story. Okay, so what happened, some people came along. Who are there? One is Rayleigh Jeans. Rayleigh, please uh, bear with me, sometimes I make a mistake in spelling, so in short form I'll write. So one is Rayleigh Jeans, another one is Wien. Okay, so these gentlemen, what they did, they started taking the facts or the theory or the formulae or the rules of physics which was existing already. So these are the list of theories which were existing already, Newtonian laws, thermodynamics, electrodynamics. Based on that, they started coming up with a new formula or new theorem or new expression that would explain what is this black body radiation is. Okay, what happened if the black body radiation is something appears to be like this? Okay, so religion is able to explain the starting half of the curve. Okay, what I mean is he came up with his expression of a formula. Okay, that formula is able to explain the first half of the expression. Okay, first half of the results. As the energy frequency goes high and high, his expression is exploding. Okay, up to some extent, it is exactly matching with black body radiation. He said only up to certain energy, certain frequency values, I'm able to explain why is this behavior. Beyond that, my theory is failing, so I can't do anymore. Okay. For that, Wien came. Okay, what he did. Okay. Okay. Let's attack from the higher energy side. Let's try to explain what is happening at the higher energy side. Okay. So he came and what he did, he used again some thermodynamics. Okay, and he started from the higher energy side. Why is the behavior like that? And he came up with his own formulae or the law of physics that is able to explain the second half of the curve. Okay, again as the frequency is reducing, okay, as the frequency is reducing, his theory is failing to explain why is the black body radiation curve is having a bell kind of a nature. Okay, so this is a Wien's law, Religion's law, Wien's law. Okay, right. So up to some extent, okay, both of them. Let me use my black color pen. Okay, 1 minute. Both of them able to explain only the half of the curve nature. Other half they are not able to do. Okay, so that means up to that point nobody was able to explain why this black body radiation is there. Okay, right? That is one experiment. One more experiment, like one more experiment. There is no need to do any experiment. You can straight away pose that question. What is that question is? If you just take an atom, any atom, okay, let me write down that experiment too. Okay, there is no need to even do the experiment. You can straight away pose that experiment is being done everywhere now. What is that experiment is? We just take an atom, there is a nucleus, there is an electron around, there is orbits of electron around the nucleus. Okay, let's say at any given point, let's say there is an electron in the orbit, the electron is moving and doing the rotation about the nucleus. Okay, as if somebody is running around some point, some fixed point. Okay, now in real world, if you ask somebody to just run in circles about some fixed point, okay, and let's say I ask one of my students go and run in circles around a point in a ground. Okay, so what happened? That guy would fall down after some time, or if he is intelligent enough, okay, what he's going to do is he is going to run in circles, so he is nicely reducing his radius, comes very close to the center point, because I did not tell him to run in particular radius circle. I just asked him go and do rounds about a point. So what he does, he will just come close and close. After some point, he will come just round, like make a very small radius circle. And after, let's say, I did not tell him to stop anytime soon, I asked him to do it forever. What happens? After some time, that student loses all the energy and he will fall into the circle at the center. He will fall down. Okay? Because he lost all the energy and he consumed all his energy by running. Now the question is, why not the electron which is making rounds or rotating about the nucleus? Why not it is not losing the energy? For sure it is moving with a velocity. If I multiply with the half m, I will get a kinetic energy. Means this guy is consuming some energy to get some kinetic energy. Okay. And why this guy is not losing energy? Why is still doing the rounds in the same circle? Okay. If at all, if we have to go to some other circle, some other orbit, okay, so this guy was pulled together or stuck to the nucleus with Coulombic force of attraction. Coulombic force of attraction. Okay, so it's as if some kind of a string is between stuck, putting electron and nucleus together. The string is an electrolytic force. In order to put the electron out of this force of misery staying close to the nucleus, somebody has to stretch the string and put it somewhere else. Where? To the next orbit. So to do that, what? Somebody has to give some stretching, extra energy, delta E energy, somebody has to give by any means. We don't know in what means, maybe heat it or shine some light onto it or hit this atom with another atom, okay, or hit this electron with another highly traveling electron. In that way, the energy of the incoming electrons transfers to this with the inelastic collision. Okay, if that is the scenario, then only the electron jumps. Okay, so now the question is, why this electron is not losing the energy? For sure, this electron remaining intact, the atom remaining stable, atom remaining stable. I'll tell you what I mean. Let's say this electron, after losing the energy, let's say if it's supposed to lose the energy, it loses the energy, it crumbles into the nucleus, fall into the nucleus. Nucleus is always trying to pull the electron towards it. Okay, so why not it is not falling? So the experimentalists posed this question to theoreticians. Till then, they were having that watermelon atomic theorem and some pudding theorem. All the laws of physics were there. They were explaining there is a nucleus, there is an electron inside, electron is rotating or something like that. They were saying. So why this electron is rotating and not losing the energy? That was also a question asked. So altogether, the theoreticians were troubled so much, they started thinking, why is this so? So Wien tried, Relay tried, okay? So other people came and they tried. They were also, in a way, struggled to explain why is this black body radiation behaving like that. Okay? That is the time, like some of our participants were pointing out, okay? Murthy Paramashivanji pointing out, Planck came along as like a savior. He just brought a new idea. What is that idea is? Planck's quantization. Okay, Planck's quantization. What is the fancy of quantization? Why people are always say, physicists say, oh, everything is quantized. Okay, so it's a fancy way of saying the things. Let me simplify. What is the quantization? What is this fancy word is? For example, we take our currency, okay, in real world, if you just take our currency, the denomination of our currency is quantized. What I mean is, we don't get, earlier we used to get Now let's say time being we have 1 rupee coin. Okay, we have 2 rupee coin, we have 3 rupee coin. No, we don't have. We have 1, 2, 5. These days we have 10 rupee coin also, and we have 20 rupee bill. We don't have a 30 rupee bill. We don't have a 15 rupee bill. We have 50 rupees bill. We have 100. There is nothing between 50 to 100. We don't have 60, 70. We don't have 80, 100. And again straight away 200. Yes, we have. And we have 500. After that, probably we used to have 1000 earlier, but nowadays we don't see. There is 2000 rupee bill. Again, that was reduced to very, very minimal these days. So this is the quantization of our currency. It exists only in particular format. Okay, bills, currency bills. So that is the quantization for us in real world. When it comes to here, in the microscopic world, okay, what is quantized is the energy is quantized. I'll tell you what is that. Okay, right? So in our real world, let's say I want to give something and take something, some business I want to do. Okay, let's say I go to a market. If I want to buy some vegetables, I can't give 15 rupees one bill. I can't give. I have to take 10 rupee bill or 10 rupee coin and 5 rupee coin together I have to give, and I can do the transaction for 15 rupees. So transaction is always constrained by the existing denomination in our real world case. Okay, so I can't do a transaction for 7 rupees or 7 rupee with 7 rupee bill because there is no 7 rupee coin, something like that. Okay, I always have 10 rupee. You can give 10 rupee and get back 2 plus 1 rupee or 3 1 rupees I can get back, and I do a transaction of 3 rupees, 7 rupees. Okay, so in the same way, the energy is quantized means energy would exist in the form of certain currency kind of a denominations. What are the denominations is, see, in our real world, what is the smallest denomination in the existing currency transactions allowed to current transactions is 1 rupee. Half a rupee, a quarter is gone now. They don't accept these days anymore in any place. If you still have, you have to give it to bank so that they will add it as a virtual amount to your accounts. Okay, let's extreme that kind of a situation we'll disregard. We'll talk about starting from the smallest denomination in the energy, sorry, currency case we have is 1 rupee coin. Similarly, everything else after 1 rupee, I am just clubbing all 1 rupees, I am creating the highest denomination. Like two 1 rupee coins together makes 2 rupees, 5 rupees, so on. In the same way, the smallest denomination energy can exist in any transaction in the microscopic world is quantized. They say the smallest denomination could exist is actually called photon. Okay, right? And he said, I can't divide the energy of photon anything smaller than that. I can't divide. Just like I can't divide my 1 rupee to 2 half rupees because that is not allowed in a day-to-day transaction these days. The smallest denomination in real world is for me 1 rupee coin. Okay, right? 1 rupee coin. See here also, if I have to have a smallest possible energy, okay, which is going to be a 1 photon. Okay, now energy means what? Which travels from one point to other point. Okay, so the example would be an electromagnetic wave, EM wave. Okay, so EM wave is a energy quantity which goes from one point to other point. It is generated from one point, it goes to other point. Okay, right? So this EM wave, if you just take a EM wave, electromagnetic wave radiation is coming. Okay, if you use some filters, basically filters are just some kind of a obstruction creators. So they reduce the intensity of the light to a very, very smaller extent. How? It's like I have a very bright light is there. I use a glass shades to cut down the intensity coming into my eye. What exactly they are doing? They are actually streamlining, means reducing not too much of light going through the filter. Okay, possibly the intensity got reduced. Okay, probably I'll have something like this, same frequency, but intensity got reduced. Okay, now if you see what is happening is, if electromagnetic wave is consisting of several billions of photons, those photons are actually coming through the filter. Filter is removing those half of photons and only sending remaining half because of this thick filter. Okay, so if I choose the idea of energy can exist only in terms of photon, it makes sense for me to understand. So that is what Planck explained. Energy always travels in the form of quantized form. What I mean is, it travels in the form of photon. Photon is the smallest possible energy, smallest possible energy denomination, I can say. Okay, there is nothing smaller than that. And Planck said, do you want the exact number, how much energy one photon carries? Let me give you that energy, which is energy is equal to, and he said it is directly proportional to the frequency with which the electromagnetic radiation is being generated. Now the question is, what is how the electromagnetic radiation is generated? Okay, let me tell you how it is generated is, they say there is a dipole, there is a positive charge, there is a negative charge. They are attracted and they form a dipole. Okay, what I will do, I will stretch them just like a string and leave it. Okay, so once I stretch them apart with my energy and leave it, so once they stretched, they don't want to be stretched, they want to come back and remain close to each other. What they do, they come back to each position, the same position after I leave them. So they come back and then remaining close to each other. I'm stubborn guy. I'll stretch them again. So basically what I'm doing, I'm making the dipole to oscillate between very stationary position to unstationary position. It is oscillating. In the same process, I am giving the energy to the dipole, and dipole is because of my energy. It's once it takes energy with the stretching, after it comes down to steady state energy, equilibrium energy, it has to lose the energy. It is just like a pendulum oscillating. I just stretch the pendulum and give the amplitude. The pendulum makes an oscillation, right? So with my amplitude, how much I stretch, accordingly the oscillation takes place. Same story, when the dipole oscillates, it emits the radiation. That emission is the electromagnetic radiation, emits the EM wave. Okay, now I'm sorry, I have a bad cold, bear with me. Now if you see with what frequency I was doing the stretching, I'm every time I'm just making the stretching with it comes close, I'll just stretch. Comes close, I'll stretch. So I'm making an oscillations with my hands, let's say. In the whatever frequency with I'm just doing the stretching, in the same amount frequency, it emits the radiation. So that radiation is equal to Planck's constant multiplied by frequency. The same thing, I multiply it and divide it by 2 pi. I can express that as a h cut by h cut into omega, where omega is angular frequency, h bar or h cut people call is a Planck's constant by 2 pi. Okay. So this energy is the smallest possible energy for any radiation to start with. You can't have a smallest energy. Now, if you bring that idea of a photon being existing, which means electromagnetic wave, when I say it is not just a wave traveling, it is just like a particles of photon traveling. Okay, they are traveling, they're hitting a filter, comes out few photons after some time here and there. So that is what quantization as per the Planck. Okay, Bohr was there. Bohr actually introduced earlier his model. Okay, Planck is the guy who actually brought the idea of energy being quantized. The, the moment you bring that idea, okay, if you bring that idea, which means the radiation cannot travel in a very increasing continuously, means I cannot have a 10 joules and 10.5 joule photon. I can't have 11 joules, 11.5 photons traveling together. I can't have that. Okay. What I will have? Either I'll have set of 10 joules photon, set of 11 joule photons. By mixing, I may create pulse. That is a secondary thing. Okay. To start with single frequency photons, I'm going to have only single denomination based photons in my electromagnetic stream. The moment you use this quantization idea, everything falls into the picture. Planck was able to explain with his quantization method, he is able to explain exactly why the black body radiation is behaving so. Okay, let me use a green color. Okay, so he is able to explain with his theory of quantization. So this is the Planck's law. Okay, so entire black body radiation falls into the picture. The experiments were able, like, he got an equation, an expression from his quantization. As per that equation, okay, actually it's a probability distribution equation. That equation exactly matches with the experimental distribution of black body radiation. Okay, so that is the quantization for you at a very early stage, when classical physics, the laws of classical physics were failing to explain, okay, the black body radiation. And also the moment you introduce the Planck's idea, as per the Planck, what happens? If you supply a photon of energy h mu, which exactly matches with the separation between two orbits, in that situation, what happens? The photon is absorbed by the electron. The electron may jump to, I am not saying certainly it jumps, it may jump to excited level by consuming that photon. So that is happening. So the energy of separation is the key here. So remember, electron cannot exist anywhere in between the orbits. Remember, electron is not like just a walking from lower orbit to higher orbit. It is not walking. It just disappears from the lower orbit, appears on the higher orbit. Okay. So for a very long side, like a zoom out manner, if I say, it appears to be doing oscillations from ground to excited and excited to ground, as it cannot exist in an excited state forever, because excited state is unstable state. Okay, if there is a hill, very point hill, okay, on the left side you have a ground state, on the right side you have an excited state. Let's say there is a very small steep towards the ground state. What happens? If somebody is standing here, he has to fall down. Okay, so let's say on the other side there is not much steep. Okay, right, something like that. Let me clear that. Okay, now because of this, what happens? If anything standing in between has to fall down to ground, so the top position is always unstable. So things has to go to either up or down. So this is a classical example just for giving a picture. So in real world, what is happening at a microscopic level is electron disappears from the ground, appears at the excited, yes, disappears at the excited and comes back to the ground. So the having energy separation and the photon energy coming in is the key to put the electron from ground to excited. Okay. So and one more conclusion was given was Bohr said if at all if the electron is revolving in a certain specific orbits, for example, the orbits have an angular momentum L, which is R cross M into V. Okay, M into V is the linear angular momentum. R is the radius of the orbit. The L is quantized with the Planck's constant. If L is equal to some integer units of H, Planck's constant, if that kind of a thing happens, Bohr said, oh, these orbits are very special. These are like a heavens. If somebody runs in that orbit, they are never going to lose the energy because there is no resistance in that orbit. There is nobody is asking for energy in that orbit. Nobody is losing the energy. So electron can run forever only in that quantized orbits, special orbits, angular momentum quantized orbits. Okay. So with that, the answer for a question why do the atoms are stable, that is also answered. Okay, right? So atoms are stable because, right, the orbit's angular momentum is angular momentum. You can even get energy from angular momentum. Okay, angular momentum is quantized. Okay, fine. So these are the like atomic stability, black body radiation are the two basic experiments. And there is one more interesting experiment also was done around 1900 only, that is photoelectric effect. Okay, I'll tell you what is this photoelectric effect. What is this is we all played caroms, we all most of us played billiards or snooker. Okay, and even 90s and 80s people have played with the marbles. Okay, during the childhood, you know what happens if I have a metallic film, let's say metallic film means it's made up of metals. If I shine a light onto this film, okay, I can even expect some electrons coming out from the film. Okay, so there is some equipment which can detect electrons coming out when a light is shining. Very good, that is a good thing to have. I take the energy, get material out of it, like conversion from energy to particles or metals, sorry, material. Okay, very good. And what they thought, okay, this a particular metal is there. I want more number of photons. Then what I can do? So anyway, Planck said, okay, so energy is quantized. So I'll have particular frequency photons coming in. So they are giving some amount of energy. I want more photons. What I will do? See, the red light frequency is very, very small. Photons are there. Energy wise, they are small in energy. What I will do? I will shine with the blue light. because the blue light photons are more energy. Obviously, they will able to they must be able to knock more electrons. Okay, so the simple idea is the 50 joule photon able to knock out one electron from the film. Okay, fine. The observation is done. This time I want two photons. What I will do? I will send 100 joule photon onto film. So my understanding is 100 joule photon is having a double energy. It must be able to knock. Okay, must be able to knock out two electrons. Obvious, right? Okay, it's fair game. I can ask that. Okay, so that is what people were thinking back then in 1900. Okay, it's like I have a very strong boy. Okay, in my class there are huge boxes. Okay, one if a weak person like a moderate student is there, he can only carry one box. If a very strong boy is there, he can carry two boxes. There are two boxes somewhere I want to transport from one place to other. Instead of sending two boys, I will send the strong boy, you go and do the work for me. He will take both the boxes and put it from one place to other. That's fine, right? Instead of disturbing two people, I'm disturbing only one person in my class. That was my understanding of classical way of seeing things, real world. But the thing is, even if you knock the material with 100 joule photon, I don't see any electron coming out. Strange. Okay. I thought, okay, one photon, maybe it is having some problem. Let's send two more photons of 100 joules. Let's send some 1000 photons of 100 joules. Let's send some billions of photons of 100 joules onto the film. Okay. You see now, interestingly, the electrons were not at all knocked out from the material. You know why? So the electrons were stuck to the nucleus, okay, with certain amount of energy. In order to electron to come out from one orbit to other orbit, I should give an energy of delta E, separation which is equivalent to two orbits. Let's say it has to come out completely. I should give just more than delta E so that electron just comes out of the atom. So this delta E of knocking out of the atom, excitation, complete excitation is fixed. It doesn't matter you send so many photons more than of this energy or less than of this energy, you are not going to see any electrons emitted out of this metallic film. Okay, so this was the puzzle back then, was given as an experimentalist to the theoreticians. Okay, so this was later using the Planck's idea. Einstein came. Okay, he took the idea of Planck's quantization. He explained this photoelectric effect, saying the energy, incoming energy must be, okay, incoming must be equal to excitation energy. Then only there is a knocking of electron. Let's say that not just knocking, that electron should also travel with some kinetic energy. Means come out of the atom, na? So the incoming energy must be slightly more depending on how much kinetic energy you need, that much of extra energy it should carry. Otherwise, I don't see any kind of electron emission. So the amount of energy required to knock they call it as a work function. Okay. Beyond that, whatever extra energy you are giving, very small, remember, not like a double. Okay. So that would be used for kinetic energy. So basically, all the three experimental results which were there, okay, right? All the experimental results which were there, black body radiation, photoelectric effect, you see, The photoelectric effect is there. Okay, no emission when the photoelectron, no emission of photoelectrons, even when I incident with the 100 joules of photons, when separation between the ground to the excitation state is just 50 joules. Okay, right? So there is a low energy incident light, few photons, even few photons of suitable E could knock out electrons. Doesn't matter, only few can also do. 50 joules of energy photons, even few photons can emit few electrons. Similarly, if I need to have more electrons, what should you do? Incident more, okay, more number of photons, but not, okay, few photons of higher energy. Okay, remember that. Okay, so Einstein explained there is a match should be there between incident photon energy and the energy separation between the orbits. Completely valency orbit from the, okay, from excitation orbit. Okay, so this is the, okay, let me go further. Okay, so that is the point when people started explaining the experimental results were connected to the macroscopic world. Black body radiation is connected to the macroscopic world, okay, and photoelectric effect, right, and the atomic stability, all are connected to macroscopic world. Okay, so people were able to understand and explain the moment Planck brought in this idea. The next contribution came from de Broglie. What he did is, okay, he brought in the new idea called, you see, quantization is there in the energy, means the energy acting like a very small denomination photon. Okay, so energy is behaving like a particle. Okay, which means, is there any way I can see in real world, can I have a material behave like an energy? Question. Okay, question is, energy is behaving, means waves are behaving like a particles, waves are behaving like a material. Now the question is, do material can behave like waves or energy? That question some people started asking. Okay, not only that, you remember, let me tell you one simple example. Okay, when you take an electron source, let's say I have a source of electrons, let's say I have a gun which emits the electron instead of bullets. If that you take those electrons, hit the some crystalline material, okay, there are atoms in the crystal, okay, what you see is as if I see the like electrons hitting and just deviating just like a waves. That is one experiment. Another experiment is, okay, you just put the electron inside a box. Let's say I have a box, a one-dimensional box. One-dimensional, remember, I'm just exaggerating into a rectangular shape. Let's say I put the electron inside a box. So let's say there is an electron. Electron for me is a material. It's like a very tiny ball I put inside. Only restriction I have put is electron can only move on forward or backward. Let's say there is a space x, position x, it moves like electron can go from 0 to L. That's all. That is the only possibility. Now what I'll do, I'll just make an observations of finding where is this electron guy located at every instant of time. Okay, let me make an observation. What happens, let me use my notes at this point. Okay, I'll give a break after 5 minutes. At 5:10 or so, I will take a break. Okay. So let's take a box 0 to L. Okay, 1D box. I'll say 1D box. And electron is there inside. Now what I'll do, I'm an interesting person. I want to more curious. I just try to find where is this electron guy located. Okay. So when I see once he is there at the very left end. Okay, fine. It's an electron. It doesn't have any higher energy. Then I thought, okay, let's keep quiet. Let's see. After some time, I see this somewhere else. What is this? This guy is left extreme once, right extreme once. How is this so? I doubt, okay, there may be some culprit who is giving the energy to this electron. Probably the surrounding walls have some temperature, okay, and that temperature is given to the air inside this box. That air might have given some air particles, might have given some energy. What I'll do, I eliminate all the inside material air and make it into vacuum. Okay, right now I put an electron inside a vacuum, and I am doubtful about the surrounding surface. I'll reduce the temperature of the surrounding surface to, let's say, absolute zero, ideally. In that case, I presume myself, yeah, I have not created any energy supplier to this electron because I removed every guy. This time I'll make an observation. I see electron somewhere else. Okay, fine. What is this? This guy is moving here and there. Now I make some thousands and thousands of observations, and every time I'm not seeing in one place, every time I'm seeing in another place. Let me plot down where is this guy located in all my observations, because these observations are repeating. So I see a pattern of this guy existing in some location. Okay, right? Okay, wait a minute. Okay, just a minute. Let me make it more. Okay, right. So wherever there is a peak, what I see is this electron guy is actually sitting there. Means I saw him sitting there in that position. Very good. And there are locations he is absolutely not existing in that locations. What is this? How come this guy is not existing in that location? Okay, for sure at the edges he is not existing, but after some time his presence is maximum, and then it reduces, and then he again picks up. And if you see this kind of a behavior, okay, so the presence of electron in space is oscillating from absolute zero presence to some maximum presence in a probabilistic manner. You see that the presence is decreasing as you come close to the wall, and then decreases and then again picks up. Okay, so let's say I'll get some functional form. Let's say some functional form I have f of x. Okay, I'm a curious guy, like I said. Let me take a square root of this function and see what would be the behavior would look like. Okay, what I see this time, okay, the behavior of this one is some kind of a oscillatory curve. Okay, what is this? Earlier I was thinking the left hand side peak and right hand next peak is more or less exactly same. Probably they should have, okay, they should have same behavior. But the thing is, when I take a square root, I'll get a plus and minus sign. So the functional form, which is plus and minus form h of x, is this kind of a oscillatory curve. It is some sinusoidal curve with some propagation constant. it appears to me like a wave for me. What I mean is, you just tie a rope between two ends and you create a disturbance. That disturbance travels like this and hits and comes back. Okay. So what is this? Electron presence is described in terms of some kind of a wave nature. Okay. So electron presence is shown as if it is a kind of disturbance traveling in space. What is that? That is the pure definition of a wave. Okay. So from that point, people said, if I go for a very, very tiny things, smallest entity, if I go, I see that smallest entity is not going to keep quiet. It can get some energy. Because of that energy, its presence is not fixed. The presence is going to be everywhere. How do I know? To find out what is the probability distribution of that presence, I would get a nice a curve. Okay, a positive curve. By the way, you see, it's a positive curve. That curve, if I just take a absolute square root of that, have oscillatory function, which is like a wave, a mathematical oscillatory function of a sine and cosine. They call it as a wave function. Why wave function? It is replicating some kind of a mechanical wave kind of a behavior. Since a wave is a concept, it is a mathematical function. They brought both together and created a concept called a wave function. So the wave function is appeared into the picture. Now the question is, the moment I have a wave concept, wave means it comes up with its wavelength. Okay, what is the wavelength for this particular kind of a wave? That is in fact connected to its mass of the particle and velocity with which it can move. All right, it's indirectly, wavelength is indirectly proportional to the mass of the particle, indirectly proportional to the velocity of the particle. You know why? Instead of putting one electron, let me put a molecule inside a larger entity. In that case, what happens? Wavelength got, okay, reduced. Means instead of having a very large wavelength, I have a small wavelength as the mass is increased. Okay. Now, as a de Broglie came, let me give a mathematical expression for this wavelength, which is inversely proportional to mass and velocity. And he said, let me divide a Planck's constant by mass and velocity. Units of that is a wavelength, meters. So he called it, that is the de Broglie wavelength. In a way, he connected the material can behave like a wave provided its size is very small, its velocity is close to the light velocity. Okay, so just for a clarification for you, you just take an example or scenario, not an example, let's take a scenario. Okay, a moving bullet. Okay, try to find de Broglie wavelength of a bullet, which comes out to be something like minus 25 meters. Very, very small wavelength, almost negligible. Okay, and when you go to a, let's say, cricket ball, which is about 10 to the power of minus 10. You know why? The mass is few kilograms, 10 to the power of minus kilograms. And velocity what? In few meters per second. In the numerator, what I have? 10 to the power of minus 34. So, obviously, the de Broglie wavelength for a ball is 10 to the power of minus 30. For a bullet is 10 to the power of minus 25. But for an electron, comes out to be 10 to the power of minus 10, which is a measurable wavelength. Okay, so de Broglie said, of course, everything in the universe can have a wavelength associated, wave nature associated, but there is a catch. You have to give an equipment which can measure its wavelength. But the problem with the smallest wavelength is we can't have an equipment which can measure such a wavelength. Only a measurable wavelength is around the optical scale, which is about few angstroms. Okay, so only that is the why, because of that micro entities would only show the de Broglie wave, would show the wave nature. Okay, right? So what kind of a wave nature? This is a wave nature. Okay, so that is what I meant in my presentation. Let me, okay, fine. So I did use a small h of x for representing probability distribution, but here the wave function is h of x. Absolute square of this one is f of x. At any given point, this is a probability distribution. Okay, so I would showed you what is a wave function would look like. Absolute square of a wave function would look like. Remember, since we are talking in terms of probability distribution, all the probabilities should sum to 1. Means since the probability distribution is varying continuously here, you should have an integration of minus infinity to infinity. All the probabilities must sum to 1. So that is actually normalization factor, which will come. In our case of qubit, you see, in the case of qubit, we have absolute square of alpha, absolute square of beta is equal to 1. What is that? We have a discrete summation giving the total probability sum is equal to 1. Okay, I'm sorry, I should give a break. I think Manoj sir is appearing just to remind me that. Okay, we'll just take a quick break for 5 minutes and then we'll reassemble. Thank you, Manoj sir.
Thank you, sir. Thank you, sir.